Something I don't mind that. I'm gonna do it on the days we have like short classes, so. It's like. You're losing water. Yeah. The other one. Why would you put your straw back in there? Grab the big one. It's in. It's in. Something else I'd want on the.
Is there anyone that hasn't gotten their exams back?
I wasn't that very good into one of the last name. Also, there's these.
Catherine? Rachel? Someone had a question on ABC. I use a regular 90, 80, 70 rating scale. So on the exam, if you combine exam one, the take home in person, there were 13 A's, 2 B's. Any questions on anything? Were there any surprises on the exam? Summers, was there a surprise on the exam or was it?
Oh, no.
Oh, it's because you were asking ahead of time.
Yeah.
I didn't think I was. And we covered the first 2 sections of chapter 4. And that's the first module in that group. 6. So you want to finish or complete module 6 and 7 this week. Module 6 is 4.1 and 4.2. Um, 4.3 is not too bad, multiplication and conditional probability. 4.4, 4.5, 4.4 I think is a confusing one. 4.5 just throws it all together. So we'll see how it goes. But I probably, if I did any of 4.4 on an exam, it would be on the take home. That way you don't have to memorize combination, permutation, and you could talk amongst people and see which one it should be. I will use more of the parts that we need, like contingency table. But I'll make an outline just like last time. Okay, 4.4. And some of this we already talked about when we were going over the other part. So independent events are events for which the probability of the first occurring does not affect the probability of the second one occurring. If we toss the coin and then roll a die, having a heads isn't going to affect the outcome on the die. It's not going to change its probability. Each value is still equally likely. If we toss a coin and then toss it again, each time it's independent of the other. It's not going to change its probability. Case where it could change the probability is this one here. When we draw a card. We have a deck of 52 cards. When we draw a card, if we don't put it back, now you've changed the probability because there's not as many cards. So as long as we're putting it back, then it's still an independent event. So you want to think of those things when you're doing the probabilities, because if it changes that probability, you need to take that into an account. But in this case, it's still independent because we're putting it back in. When two events are independent, the probability of both of them occurring, probability A and B, you can just take the probability of each of them and multiply them together, as long as they are not changing each other's probability. Well, the first. That's okay. So toss a coin and roll a die. We said they were independent. Probability. What is the probability? Well, since these are independent of each other, we can take the probability of a head and multiply it times the probability. What is the probability when you toss a coin that it will be a heads? One is one. Now, rolling a die can be the numbers 1 through 6. If we're rolling a number less than 5, how many possibilities are there? 4 out of 6. Could have reduced the 4, 6. Multiplying across. Four out of 12. Just another way of looking at the probability. We could have looked at the whole sample space. Heads and the tail, and then So there's heads with all six, a tail with all six, which gives us 12. And we wanted heads and a number less than 5, which is 1 through 4, which is only these 4 out of the 12. So you can list the sample space, but if it gets too large, that's not going to be a possibility. Any questions on that one? A card is drawn from a deck, replaced, and another card is drawn. The probability of a king and then a 7. Because we're putting the card back in, we're not changing our probabilities. There's still 52. So we can find the probability of the king times the probability of. What's the probability of pulling a king? There's 4 kings out of the 52. What's the probability? It was just a 7. Probability of pulling a 7. How many 7s are there? Just 4. There's 4 of each. What's 52 times 52? Or maybe reduce them first. On Alex, you have to reduce them. Any questions so far? It was found that 3 out of 4 people who commit a bank robbery are apprehended. If 3 bank robberies are chosen at random, I wrote the answer in there. Find the probability that all 3 are apprehended. Okay. You can find each separately. So if there's more than one thing happening, as long as they're not as long as they're independent of each other, you can keep multiplying on. In this case, then we can take 3/4 times 3/4 times 3/4. And we used that process when we found the number of winning coin tosses per game. So it was 1/2 times 1/2 times 1/2 times 1/2. And you could just keep multiplying as long as the one probability will not change the outcome of the other one. Any questions on that? Dependent events, events for which the outcome or occurrence of the first event affects the outcome of the second one. So the probability changes. A card is drawn and we don't put it back in there, then when we go to draw another one, we don't have 52 cards, we only have 51 cards. It changes all the probabilities. So they're dependent on each other. The second one depends on what the first one did. If you draw a marble from a bowl and you don't put it in back in, then there's less marbles, and whatever color you pulled out, there's one less of those. And so you're changing all of the probabilities. That makes it dependent on what happens first. For that, there's a second multiplication rule. When 2 events are dependent, the probability of both, this symbol here, that line, That means given. We'll probably write it below. So it's the probability of B given A. So it's written, probability of A given B. Oh, there's a formula, but before we get to that, you can do it without the formula. Three cards are drawn from a deck of 52. The probability all three are jacks. How many jacks are there in a deck of cards? Anyone? 4? Right? Now we're pulling a card, we are not putting it back. What's the probability the first one's a jack? 4 out of the 52? No, we pulled a jack, so there's only 3. And there's only 51 cards. So we've changed the next probability. So given this occurred, what's the probability the next one's a jack? 3 out of the 51? Given that the first 2 were jacks, what's the probability of the next one's a jack? Well, we got rid of one of these, so there's only 2 left with 50 cards. So even though we're changing the probability, we still can use the same process. Just make sure you're thinking about how it's changing your deck of cards or your bowl of marbles. And 24. Any questions on that? Most calculators will reduce a fraction for you. On the TI-83 and the T-84, it's under the math button. So if you take 24 divided by 132,600 and then hit the math button and enter twice, it will reduce your fraction. I don't know how to do it with the other calculators, but I think they can. I think all you do is divide it and then tell it to give you a fraction and it'll give you it in reduced form. On the test, it does not have to be reduced, but Alex wants it. Okay, go ahead and find the probability of ace, a king, and then a queen. If you need the deck of cards, you can bring it up on your phone. Just put image of deck of cards and a. Define both the probability of an ace, king, and then a queen, and then the probability of 3 face cards. You're getting on this one 64 out of the 132,600. Yeah. An ace, there's 4 out of the 52, but then I'm gonna pick one, so now there's only 51 cards, but there's 4 kings. And then I'm going to pick a king, which means there's only 50 cards, but there's 4 queens.
No.
Oh, okay.
That makes sense.
I did it in my head. I shouldn't do that. Any questions on it? Three face cards. How many face cards are there? 12. There's the king, a queen, and jack in each suit, so there's 12 of them. So the probability, the first one is a face card, 12 out of 52. But we picked a face card and we didn't put it back, so there's 51 cards and only 11 of them are face.
Assuming that we're picking.
Right, we're assuming each time that we're picking it,
Uh.
the correct one. So the probability that the first one's a face card is 12 out of 52. Now, assuming this happened, the probability of the next one would be 11 out of 51. Assuming that happened, then there's only 10 face cards left out of the 50. Any questions on that? So what you're doing is you're finding the probability of the next one, given that the ones before happened. Any questions? Now, the probability of B given A, it does have a formula. You take the probability of A and B and you divide by the probability of A. A is the given part. So if we look at this contingency table, and 100 people were asked whether they are a dog or a cat person. I don't know, I just got it off the internet for a study. So you go across, it's telling you there were 52 male and 48 female. Going down, it tells you how many were dog person, 51, and how many were cat person, 49. Going across and down on your total should add up to the total number of people, which was 100. There's two ways you can do given probability. I'm going to show you with the formula and then without. So the probability they like dogs given they're a male. We use this formula. It would be the probability that it's a dog and a male divided by the probability it's a male. So the probability it's a dog and male is 42 out of the 100. Because there's 42 male that chose dog. So male and dog would be 42 out of 100. The probability male, there's 52 out of 100. The hundreds will cancel. $42 out of 50. Any questions on that? So that's one way of doing it. And when you're not given a contingency table, when you're given separate probabilities for each case, you would have to use this. But when you're given a table, I'll show you another way of doing it. The way the hundreds are canceling, when you're dividing by a fraction, you can flip it and multiply. And of course, this could reduce. So you're just flipping this and multiply. Another way of doing it, when you have a contingency table. We already know it's a male, so only use that row. We know it wasn't a female, we can just forget about that. So since male was given, we only use the row for men. There's 42 out of the 52. So with a contingency table, and we're going to do a lot with contingency tables. So you do want to make sure you understand the contingency tables. It's an important section.
Do you have to put the 52 out of 100? Like, do you need to do that?
You can just do this.
Okay, that's absolutely.
Yeah. There's, I think it's called goodness of fit, and use a contingency table for all kinds of testing, strep throat, drug testing. They use contingency tables, and then you find different probabilities. So we'll use it a lot in the later chapters. I recommend this way. If you need to know the formula for certain cases, but for a contingency table, you don't. Okay, so if we have the probability dog given male, what's the probability of male given they like dogs? Is it the same?
No.
Yes, no. No,
No, the total, yeah, the table changes.
because we know now it's given dogs. So we're only going to use that column. So since we know the one we picked is somebody who likes dogs, we're only going to use these 51 that like dogs. See how it's changing our probability. So by knowing something ahead of time, we get a little better probability. But you only use that part then. So given they like dogs, and what's the probability it's a male? 42 out of the 51. Still reduces. So depending on what's given, probabilities are different. You need to be careful. Some might come out the same, but very rarely. Any questions on that? Need to do another one. Try one. Probability, it's a female given they like cats. Let's find both.
Wait, which one?
So for the first one, we know they like cats. So it's just this column. So we're only using 49, because we already know they like cats, female 39 out of 49. Yes. Yeah, maybe. No. We know they like cats, so there's 49. Female that like cats is 39 out of 40. So whatever's given, you only use that row or column. In this case, cats is a column, so we only use that column. So we're only using this spot, not these. Won't let me highlight it, I guess the way I pasted it. But we're only using these. The female's 39 out of 40. Okay, what's the probability of this? They like cats given their female.
39.
Yes. Because we know it's definitely a female, we only use that row. So where there's 48 total, and 39 of them like cats, 39 out of 48.
I did it backwards.
Hmm?
I did it backwards, so it's the female.
Oh. Any questions on that?
So whichever one comes first, that's the one that'll be on top, right?
The given part gives you your row or column. So the second part, that's what breaks your row or column. So check that first and then only use that row or column. If it's not a contingency table, then you probably have to use the formula, which isn't that bad. Any questions on that? Trying to think of one that would use. We can look at that. I think they were all tables. Oh, no, I guess not. When it's cards or things like that, I would do them the way we did them. Just think about how many are left. Contingency tables, I do them the second way I showed you. Anything else where you'd have to? The class as a whole is more than 50% done. That's good. Okay. Let's look at some of these. Look at number 3. Video and computer games. 69% of US households play video and computer games. Choose 4 heads of household at random and find the probability. None play video or computer games. If 69% play, how many do not play, first of all? So if 69% play video games, what percent do not play? 1 minus 69% is 0.69, gives us 0.31 or 31%. Depending on what Alex is asking. The probability none of them play, just multiply each one together. Each time when we pick a person, there's a 31% chance that they don't play games. Kind of like tossing the coin over and over again. Or 0.31 to the fourth. Now, they said to round everything 3 decimal places unless it's a lot of zeros. So it would be 0.009. So when you're finding a probability that you're writing as a decimal, you go 3 decimal places. Probability all 4 play. Playing games was 69%. We're picking 4, so 69 to the 4. 69 times 69. 0.227. Any questions on that? A Gallup poll reported that 52% of Americans used a seatbelt the last time they got into a car. I think that's low. If 4 people are selected at random, find the probability that they used a seatbelt the last time they got in the car. So all 4 use a seatbelt. Point 21 to the 4. Not very likely. Any questions on that? And someone will have to get on her. It is reported that 72% of working women use computers. Choose 5 women at random. Find the probability that at least one does not use a computer. %72% use computers. What percent do not use computers? Anyone? Because it has to add up to 100. Remember the complement, 1 minus? Just in case we need it. So the probability that at least one does not use a computer. Looks like chicken scratch. So that means at least one doesn't use it. Could be 1, could be 2, could be 3. How many are we picking? I think 5. So there's a lot of different cases if we're going to find all of them. What you'd have to do is do it with one of them, then 2, then 3, then 4. But there's only one case that's not in there, right? Because if at least one doesn't use the computer, we could take 1 minus the probability all 5 use the computer. This is a case where you want to do the complement. Rather than having, because what you have to do is add them each together. You'd find when one doesn't use the computer, 2, and find each of them and add them all together. But there's only one that doesn't fit the case, so subtract that one. Probability of using is 0.72. 5 of them then would be 0.72 times 0.72 times 0.72, or take it to the 5th. Going 3 decimal places, 0.807. They should put B before A. B is the probability that all 5 use the computer, and that would be just the 7.72 to the 5th. Which is 0.193. And notice that this and this add up to 1. Any questions on that? 0.72 to the 5th. So all 5 use a computer, 72% use a computer, so each time we pick one, it would be 0.72. And we're picking 5, so we took it to the 5th. Any questions on that? Sometimes those get tricky, the percent one. Like the marbles are nice and straightforward, just think of what's in each one. But the percents are a little harder. So if there's any you have questions on, just send me a picture, and we'll go over them. We will finish chapter 4 tomorrow.
Yeah. Yeah.